in today's session, let us discuss about the drawing of shear force and bending moment diagrams for cantilever beam subjected to uniformly varying loads and combination of these loads, the various loads acting. When the sign convention, this was discussed in previous sessions also. Left up, right down, positive. Left down, right up, negative, regarding the direction of forces. And bending moment, the sign convention is sagging, positive, and hogging, negative. Okay. Consider the cantilever beam. Cantilever beam means one end fixed, the other end is free. Okay. Yes. So in cantilever beams, the reactions need not be calculated as in the case of simply supported beam. Okay, because here we have an option to consider the free end side. Okay, free end side, if you consider for calculating the shear force and bending moment, it involves no reactions. Okay, if you consider fixed end side, then the reactions are required. Otherwise, we don't require the reactions to be calculated. Okay, so we can consider always the free end side in case of a cantilever for calculating the shear force or bending moment. Okay, so in this case also we consider one section between AB, and only one section is sufficient here because it is continuous loading distributed. Okay, so one section is sufficient here. We consider the section at a distance of x. Okay, at a distance of x, and we find the intensity of loading here, which is calculated by using the property of similar triangles. Okay, taking this as W dash and this as W. W it is given already. Okay, so here W dash by W is equal to x by L. That is the property of similar triangles. Ratio of corresponding sides is equal. So from this you will get W dash equal to W into x by L. Okay, W into x by L. Okay, and now let us consider the shear force at section x. Shear force at section x, considering right hand side, we have only the loading, downward loading, so it is positive shear force. And what is the total load to the right? That is nothing but area. Area is half into base. Base is x and height is wx by L. So it is wx square by 2L. It is positive shear force, and x varies from 0 to L because only one section is sufficient. Okay, at x equal to L, 0, we get shear force at A by substituting x equal to 0, and which is 0. Okay, and at x equal to L, by putting x equal to L, we find the shear force at B, and that is equal to WL by 2. WL by 2. Okay. Similarly, we find bending moment at x. Bending moment at x is negative here because it is a hogging bending moment. A downward bending you will have. Okay. So bending moment is negative. What is the bending moment here? The total load is half into base into height Wx by L into the distance of centroid, which is x by 3 from base. Okay, so you will have Wx cube by minus Wx cube by 6L minus Wx cube by 6L. Okay, so here we find bending moment at x equal to 0 and at x equal to L. Bending moment at A is 0 and bending moment at B is minus W L square by 6. Okay, minus W L square by 6 at fixed end. Bending moment at B means bending moment at fixed end. Minus W L square by 6. Okay. Now, these 2 points are not sufficient to draw the curve because it is a parabola. Okay. Similarly, shear force also varies parabolically. Kada? So, these 2 points are not sufficient. We need to find one more point in between. That generally at x equal to L by 2. At mid-span, we will find the shear force and bending moment. Because these 2 are parabolic curves, we require third point on the curve. Okay, because endpoints are not sufficient. So at x equal to L by 2, we find shear force at C. So let C be the midpoint. Let C be the midpoint at x equal to L by 2. So what is the shear force at x equal to L by 2? It is W L square by 8L. Okay, or WL by 8. WL by 8. Okay. Similarly, at x equal to L by 2, bending moment at C is, what is the bending moment at C? Substituting here, x equal to L by 2. So, W L cube by minus W L cube by 48L. So, you will have minus W L square by 48. Minus W L square by 48. Now, we have 3 points on the curve which are sufficient. Now, let us see how we draw the shear force diagram. So, shear force is positive. Shear force is positive and bending moment is negative. Okay. So, what is the shear force at A? 0. And at B, WL by 2. And at midpoint, what is the bending moment? Shear force WL by 8. So, if you observe, half of the shear force at B is WL by 4. Okay. That means if it is a triangle, if it is a linear variation, then the shear force at C will be half of WL by 2, WL by 4. But the actual bending moment at C, shear force at C is less than WL by 4. So, we have to draw the curve downwards like this, parabola, not like this. Okay, this is not correct. So, the parabola we have to draw by keeping this point in mind, whether the shear force at midpoint is less than half or greater than half of the maximum shear force at the end. Okay, similar reasoning here for bending moment diagram also. What is the maximum bending moment at fixed end? W L square by 6. W L square by 6 minus. And half of this is W L square by 12. Half of this will be W L square by 12. But what is the bending moment at C? It is W L square by 48. It is less than half, W L square by 12. So, it will be somewhere here. W L square by 48 means somewhere here. Okay? Yeah. Something like this. You will have the bending moment diagram. Here it is W L square by 48. And this is negative. This is negative. Okay, yeah. That's how we draw the shear force and bending moment diagrams for cantilever with uniformly varying load. Uniformly varying load. Yeah. Now consider another example here. A cantilever subjected to point loads. There are 4 point loads acting at a spacing of 0.5 meters between them. The total span of cantilever is 2 meters. Okay, the total span of cantilever is 2 meters. So here also we consider 4 different sections between AB, BC, CD and DE. Okay, so actually for this problem, drawing shear force diagram is simple, in the sense it requires just addition and subtraction to find shear force at different sections. So it will be easily drawn. Okay, so the shear force at the section X is, considering right hand side, it is 500 newtons. Okay, so 500 newtons is the shear force at X. That means shear force between D and E remains same. We know that because there is no load, the shear force remains constant. Next, coming to CD, the shear force at X in the second section, in the second portion CD, is 800 plus 500, that is 1300. That means there is an increase in the value of shear force. This is positive shear force. You can observe this is positive shear force. Right side downwards is positive. Okay, so here it is 1300 newtons. The load is in newtons. Okay, and this will be same between C and D. And there is again an increase in the value by 300 at C. So total is 13 plus 3, 1600 newtons, which remains same between B and C. And at B, there is again an increase in the value by 400. So it becomes 2000 at A and C, 2000 newtons. That means sum of all the forces acting towards right of section in portion AB. Okay, this is simple. Similarly, bending moment diagram also. Okay, we go on add the bending moments. Here it is only linear variation, so we can calculate easily. Okay, bending moment at D, all are negative bending moments only here. Okay, so what is the bending moment at A? If you calculate 400 into 0.5, that is 200. 300 into 1. Okay, bending moment at A is 400 into 0.5 plus 300 into 1 plus 800 into 1.5 plus 500 into 2. So it becomes 200 plus 300, 500 plus 1200, 1700 plus 1000, okay? 2700 Newton meters. And bending moment at B, is 300 into 0.5, considering right hand side, 300 into 0.5 plus 800 into 1 plus 500 into 1.5. So this is 750 plus 800 plus 150. So 950 plus 750. It is 1700. 1700. Okay. This is 2700 here and 1700. Okay. And what is the bending moment at C? Considering right hand side again, 800 into 0.5 plus 500 into 1. That means 900. Okay, it is 900. And bending moment at D is 250. 500 into 0.5. It is 250. And bending moment at E is 0. So, like this, we calculate without considering sections. We don't require sections in this type of problem. Okay. Yeah. It is simple case. Okay. And now, let us see another example. Yeah. You see this here. We have point loads and couples acting on the cantilever. The total span of the cantilever is 8 meters. The total span of the cantilever is 8 meters. Okay. So here we require 4 sections to be considered. One between BE, one between ED, one between DC, and one between CA. Okay. So here right hand end is taken as A and left support fixed end is taken as B, and in between we have 3 points where the loads are applied. Okay. Here couple means concentrated movement. Here the intensity is 30, not intensity, it is concentrated movement actually, 30 kilonewton meters. That is the moment. We don't need to multiply it again with distance. Okay. It is directly added when calculating bending moment. Okay. If it is a force to find moment, we will multiply with the distance. It's already a moment, so we don't multiply with distance. We directly add it. Okay. So considering different sections, considering section in portion AC, let us consider a separate figure here. Yeah, we have 2 point loads, one at free end and one at mid span. Okay, and the loads are 30 and 20, and the couple is also 30 and 20. So this is this is 20 kilonewtons, and here it is 30 kilonewtons, and here the moment is direction is important. This is clockwise and this is anti-clockwise. Okay, this is 20 kilonewton meters and here it is 30 kilonewton meters. Okay, now we are considering section between AC with origin at free end again. We consider free end side. Okay, so shear force at X is 20. Right side downwards is positive 20 kilonewtons. Okay, so shear force, for shear force only 2 sections are sufficient actually, because this moment will not, this couple will not affect the shear force between A and D. Shear force between A and D, that will not affect the shear force. So as far as the loading is concerned, between D and A there is no load. Couple is there. Couple means 2 equal and opposite forces, so it will not affect the shear force. Okay, so shear force, for shear force 2 sections are sufficient between AD and DB. Okay, anyhow we consider shear force also at 4 different sections. Okay, yeah, shear force now at A and at C are equal to 20. Okay, because it is independent of x. And bending moment at x, this is portion AC. The limits for x are from 0 to 2. X limits are 0 to 2. And bending moment at x is 20 into x minus 20 into x. It is dependent on x. So at x equal to 0, bending moment will be 0 at A. And at x equal to 2, bending moment at C will be 20. This is at x equal to 0. This is at x equal to 2. Okay. At x equal to 2, bending moment at C is 20. Okay. Now, consider the section between CD with again origin at A. So, in portion CD, the limits for x are from 2 to 4. The limits of x are from 2 to 4. So, shear force at x is it is plus 20 again. So shear force remains same. We add only force. We don't add this 30. 30 is moment. We should not add that. Okay. We add only force. So shear force at C and shear force at D are equal to 20. Okay. Now coming to bending moment. What is the bending moment at C? That is at x equal to 2. At C, x equal to 2. So what will be the bending moment? First bending moment equation, you write. What is the bending moment at section x? It is 20 minus 20 into x. And this moment comes into picture now, as we are considering section between CD and right hand side we are considering. So this couple also comes into picture. What is the nature of the couple? Clockwise. So which produces sagging bending moment. So it is also negative. So 20 multiplied by x, because it is force multiplied by distance, but this 30 is not multiplied with distance because it is already a moment. You should not multiply again with distance. Okay, it is directly added to the moment. Understand? So now we substitute x equal to 2. You will get bending moment at C. What is that? At x equal to 2 minus here it is bending moment at C is 40 actually. You can correct this bending moment at C considering portion AC at x equal to 2 meters, it is minus 40 actually. Bending moment at C is minus 40. Here also you consider bending moment at C is minus 40 minus 30 minus 70. It is not same. Bending moment at C is not same because of this couple. Okay, as we have seen, at the point where the point load is acting, there will be a sudden decrease or increase in the value of shear force. Same thing happens at the point of application of couple in case of bending moment. Okay, bending moment value changes suddenly from 40 to 70. Okay, at C because of the couple. Concentrated moment. Couple is concentrated moment. Okay, we can say like that. Okay, so bending moment at C is 70. Now at x equal to 4, what is the bending moment at D? Bending moment at D. So take this 4 here. So 20 into 4, that is 80 minus 30 minus 110 minus 110. Units are kilonewton meters. For all this bending moment, it is kilonewton meters. Okay. Yeah. Now consider portion DE. Portion DE. What is the shear force? X limits are from 4 to 6. The limits for X are from 4 to 6. Considering section here and origin at A only. Okay. So shear force at X in this case is 20 plus 30. That is 50. Okay. And shear force at X equal to 0, not 0, at X equal to 4, that is shear force at D, and shear force at E will be the same, 50. Okay. We consider bending moment equation in portion DE. So what is it? Minus of 20 into X minus 30 into this load. 30 into X minus 4 minus 30 minus 30. Okay. This couple all are producing anti-clockwise. Sagging moment. All are producing sagging, isn't it? Downward bending. So all are negative here. Now substitute X equal to the limit such as 4. At X equal to 4, the bending moment at D is, this term becomes 0. So when it is 4, 20 into 4 minus 30. So minus 110. Okay. And at X equal to 6, bending moment at E is, what is it? Minus 20 into 6, that is minus 120. Minus 30 into 6 minus 4, 2. So minus 60, minus 30. Okay. So minus 120 minus 60. That is minus 210. It is minus 210 kilonewton meters. Understand? Now we consider the last portion BE. The limits for X are 6 to 8. The limits for X are 6 to 8. So here the bending shear force remains same. Shear force remains 50 at E and A. At E and B. At E and B. Coming to bending moment. What is the bending moment at X? In this portion we are considering with origin at A. Now coming to this, we have minus 20 into X, minus 30 into X minus 4. This is for point loads. Okay. And this moment is minus 30 and this moment is plus 20 because it is anti-clockwise. This is anti-clockwise which produces sagging moment. It is plus 20. So you will have minus 30 plus 20 and minus 10 you will have. So now we find out bending moment at E. Bending moment at E. Bending moment at E means at X equal to 6. So you will have at X equal to 6 now. Minus 210 plus 20, that is minus 190 you will have. And there is a drop in the value of shear force from 210 to 190. And bending moment at B is at X equal to 8. So minus 20 into 8 minus 160 minus 120. That is minus 280 minus 290 it is. Minus 290 kilonewton meters. Okay. So now we have calculated the values of shear force and bending moment at salient points. Okay. Now we can start plotting the diagram. You can see the bending moment diagram. Yeah, this is the diagram. So shear force diagram is as shown in the figure. It is positive. This is positive. Okay, we draw it above because positive. So it is 20 and 50. Okay, and bending moment diagram. So bending moment at A is 0 and at C it is minus 40, and there is a drop in the value by minus 30. So it becomes minus 70 and varies from minus 70 to 110 between C and D, and 110 to 210 between D and E. And there is again a drop in the value. Here it is actually increased, minus 210 to minus 190. Okay, yeah, there is an increase here, and it varies from 190 to 290. Okay, at fixed end 290 is the bending moment. Already we have seen those values here. Just these values are plotted here. So what you need to observe in this case is, as there is sudden increase or decrease in the value of shear force where there is a point load, there will be a sudden decrease or increase in the value of bending moment also where there is a concentrated moment, couple acting. Okay, where there is couple acting, the bending moment and bending moment value will either increase or decrease suddenly at that point. Okay, depending on the nature of the moment. Okay, that is to be noted in this problem. Couple is acting. Okay, yeah. This is another example. So here you have point loads and uniformly distributed load combination. Okay, so procedure is the same. There is no difference. Okay, so here we need to consider 4 different sections, because for every change in loading, the load between E and D is, there is no load. At D there is a UDL. Okay, starting point of UDL. So from D onwards, the shear force equation or bending moment equation changes. Okay, and at C again, that is the end of UDL, and a change of loading again. So from C to B, you need to consider one section where point load is acting. Okay, so between A and B we consider one more section. So totally we consider 4 sections in this case. Okay, 4 sections we have to consider here. So first section, if you consider between DE, the limits are from 0 to 0.5. 0 to 0.5. So shear force at X is 2.5. Shear force at X is 2.5. Right side downwards is positive. The same convention we follow here also. And bending moment at X is minus 2.5 into X. Okay. So bending moment at E is 0, and bending moment at D is minus 2.5 into 0.5, that is minus 1.25. Okay, yes. Next, in portion CD, X varies from 0.5 to 2.5. X varies from 0.5 to 2.5, and the shear force now is dependent on X between CD, because there is a load distributed between C and D. Okay, So the load changes at every section, from section to section between CD. So shear force also is dependent on X. So shear force at X is now 2.5 plus intensity of load is 1 into distance. Length of UDL is X minus 0.5. Length of UDL means you have to consider this length, and X we are taking from A. So length of UDL is X minus 0.5. Okay. So shear force at D is at X equal to 0.5. This term becomes 0 and shear force is 2 point. And shear force at C, that is at X equal to 2.5. So it becomes 4.5. Okay. Similarly, we will calculate bending moment at X. Okay. Bending moment at X. So minus 2.5 into X minus 1 into X minus 0.5. Okay. X minus 0.5 into X minus 0.5 by 2. Okay. Yeah. Here we will find out bending moment at different sections. Here at X equal to 0.5, we will get bending moment at D, which is minus 2.5, that is minus 1.25 at X equal to 0.5. And at X equal to 2.5, we will get bending moment at C. Bending moment at C as 2.5 minus 0.5 is 2. 2 square by 2, that is 2. And X equal to 2.5 is 6.25 minus 6.25 minus 2, that is minus 8.25, we will be getting kilonewton meters. Minus 8.25 kilonewton meters. Okay. So like this, we will find out all the values and we will plot the diagram. Okay. The shear force diagram for this will be, let us directly draw now. The shear force diagram, already we have seen number of problems how to calculate shear force bending moment. Okay. Yeah. Now let us see how we can directly draw the shear force and bending moment diagrams. Okay. Yeah. Coming to shear force diagram here. Yeah, at E it is 2.5 plus 2.5 and it varies from 2.5 to 4.5. Okay. 2.5 here and 2.5 here. 2.5 to 4.5 here. And this 4.5 remains same between B and C because there is no load. The 4.5 remains same. And there is again an increase in the shear force. There is an increase in the shear force by 3. So it becomes 7.5 and which remains constant between A and B. Okay. Yeah. This is the shear force diagram. This is positive shear force. Understand? And bending moment diagram is negative hogging bending moment. Okay. So bending moment at A is 22.5. It is calculated here. Actually 3 into 1 plus 1 into 2 into distance is 2.5 plus 3.5. Okay. 2 into 3.5, 7. 7 plus 3, 10. And 2.5 into 4, 10. Okay. 2.5 into, sorry, it is 5. 2.5 into 5. So 12.5. So total 22.5 will be 20. 22.5. Okay, and between DE it varies linearly. Here it is 1.25, and bending moment at C is 8.25, and it is parabolic variation. Parabolic variation 8.25 to 2.5. It varies. And between B and C, what is the bending moment at B? So 2.5 into 4, that is 10, and 2 into 2.55, 15. Okay, that is 15 here. And these are straight line variations. Okay, these are straight line variations only. It is clear. So that's how we draw the bending moment diagram. So bending moment diagram in portion CD is parabola. In the remaining portions, it is straight line only. In the remaining portions, the bending moment diagram is straight line only. In CD portion, it is parabola. Okay, yeah. That's how we will draw the shear force and bending moment diagrams for cantilever beams. Okay.
Like, share and subscribe. Hit the bell icon for more updates.